from Tencent. So I'd like to share about what we've done in Linux scheduling algorithm and its optimization. So this is the background. So the server in Tencent is million level, so it's heavy assets. How can we make the full use of it? How can we better use it? Make sure it's not idled. Make sure it's fully functioning. So let's say the CPU usage ratio is only 20%. Now we try to boost it to 70%. So actually, internally speaking, the server in Tencent, we're still trying to boost the usage ratio of CPU and GPU. And actually, we'll try to boost its efficiency that's yielded and save cost. So with Docker, with containers and other means, we try to boost the usage ratio. So we have our internal KPM, and also we can also directly run our containers. We will improve the usage ratio of CPU. So we have different definitions for a CPU, and I won't go into great details here. So we cannot use it for latency sensitive pod, and we can only use it for pod that's with lots of offline threads and processings. It's mainly used for offline scheduling. We need to use the KPM internally to make optimization and improvement. And some of the solutions are trying to run the containers on raw metal machine. And so I'd like to emphasize again, for the online service, we are basically using it for latency sensitive business, and it's high reliability. And so for offline business, it's low latency sensitivity, and most of them are for computing. So the impact on one-time latency is pretty minimal for this part of the business. So for online business, for example, real-time game that's latency sensitive, they have really low reliance and tolerance for latency, and if you are fighting with the other competitors, then there's very high latency. It's unbearable actually. So, and for offline services, it's another example. If it's low latency sensitivity, then for example, If you want to check on the virus at backend or sorting your photos, then these are low sensitivity. These are the business with low sensitivity for latency. So these are offline part. It's different. So for video games, that's not a story that's highly sensitive for latency. So the CPU usage ratio is, or the load is not very high. And for the mixed deployment, that leads to a classical issue. The blue part is online series, and we have n units of CPU, and for example, task B, we need to acquire resources from A, and from C, it's dependent on log, and the origin is CPU 0, and B is occupied by offline tasks Y, and that would cause the whole sequence is chaotic, and CPU 1 to 4 to 2, it cannot be unlocked and cannot be operated. For example, Y and Z. So they have different logs. It's very complicated landscape in this pod chain. And go back to the original question. For example, how to solve this issue. Currently, different categories, different enterprises are using this platform to allocate their resources in CPU. And for example, we have a mixed deployment of online offline business, and it's uncontrollable. And this is a very fair scheduling program, and it would not show any preferences to any thread or process. And we have to guarantee all the main thread can be scheduled on a timely manner. So this is shared platform. This is lightweighted somehow, and it cannot solve our problems. And for quarter mechanism, this mechanism, if you're familiar with it, C group will provide two mechanisms setting different quarter, different function groups. And we will have high frequency timer, and try to traverse the whole C group tree, and it's very heavy. It needs heavy operation. I need to double check on the quarter, and if we set a smaller peer, then we have a smaller number of offline groups. Then we can avoid some ineffective overhead for CPU, otherwise it will be bad for the system. This is the shear and pure quarter status and issues we've encountered, and the others includes the balance load balancing. For example, in this scenario, we have 100 online limitation and 1,000 offline limitations. Then we have to separate online offline thread, and if we mix them together, then that means we add another 1,000 offline threads into this 100 online thread. Then we have to do load balancing. There will be panic, and the CPU will be migrated to CPU Y. That will cause a major impact on the terminal, and we have to change the context. And in high-level scenarios, we have around 200 entries. If we are migrating thread, then obviously that means lots of consumptions, and the load balancing is not calculating these parts. We don't have a switch to control these processes. And for example, this load balancing issue, we have to strike about in order to solve it, we have to strike a balance in mixed deployment and introduce a new categories of scheduling. This BT, we don't have a final name for it. We still discuss on that, and if it's lower than the set CFS, then we have to guarantee that the online service can operate and will not be stripped of the resources by offline parts. We have to differentiate thread, differentiate the online from offline parts, and the systems. We have to guarantee that these two parts, online and offline, are not inter-affected by each other. This is why offline scheduling is meaningful. We have CFS, we have CPU scheduling, and we have a BT scheduling, RT scheduling. Why? Because first, that means we have to change a lot of codes, and that will undermine probably the stability of the whole system. So we need to solve these problems with controllable cost. And the first principle is that we have to prioritize the online computing, and if not, in the whole designing mechanism, we have to guarantee the preemption of online service. And we add additional support from our tech side, and we add lightweighted load balancing mechanism. The logic behind is that we guarantee that the offline has their own load balancing mechanism, and online has its own load balancing mechanism as well, and we add two new interface. One is the generic interface. They can control the overall ratio of offline service, setting the top to 20%. So why do we set this limit? It's some of the pod want to do their own configuration for each set of the CPU, and we cannot allow that by setting the configuration that can control the load for each CPU. And if you don't want to do that, then you can transfer the control CPU to the mechanism of load balancing. And we have three categories: one, load balancing, and limitation for interrupt. And we will set the priority for offline technologies and offline processing and thread. And so for the limitations of bandwidth, we have lightweighted statistics and accounting. We use these minor technologies. We're not doing heavy accounting like a recorder. It's not necessary by our standard. For example, didn't have to be as precise as like 20%, 22%. It's not necessary.
And it's about 20%, so you can accept it. But yeah, this is not very important, and it's offline. So we need to make sure that we will not add a new interrupt, and we have make it compatible with norms. So to make sure that the offline, when it's 6 Hz, it is compatible. So for load balancing, it's similar to the one you have heard of, but we have this wait time here. When we are conducting this offline tasks, we need to calculate this wait time for the basis for the load balance instead of the life cycle, the balance. Yes, so the function sometimes is closed and sometimes the function lies idle. So the off load balancing, when we have this online load balancing, we won't consider the offline. But maybe the offline load balancing may be online. So we need to make sure that not to make the offline load balancing into some CPUs with high level of online load balance. This is our tricks. And based on this, our test results proved to be very good. So these two test results. So on this line, we have this online service A. So for per minute, the task, maybe we focus on the failure or success rate. One is not mixed with the offline is about 200, but with the mix of the offline, then there's an increase of 5,000. So this task, yes, for the users, they cannot accept it. And also its failure rate, it will increase from 200 to 400, but the success rate remains the same. And we can add some lightweight load balance into it. For the second scenario, it's more about the average time delay. So its average time is about 115 seconds. But with the addition of the secrets, the failure rate is increasing. And but why users cannot accept this time is because while there's an increase of about 20 milliseconds, then we can't accept it. Let's go back to this page. So for each module, there's an increase about 20 milliseconds, and this is quite a long time. Then there is a total of 120 milliseconds. Then go to this page. You can see that the time delay is very long. Yes, that's why the 20 millisecond delay has a huge impact. It's like a time increase along the whole chain. So for this, the failure rate is not increased and it's acceptable, and for the reliability is also ensured. And this is our off-balancing effect. So these yellow curves, we have not classified it. Although it does not affect the online task, but it's unpredictable. It means that the offline CPU utilization rate has not reached an acceptable level for the blue curve. It means the standard kernel. You can see that the fluctuation is not that sharp, but it affects the online task. And so for offline, it's not that smooth. For the gray one, after we have done the test, it does not affect offline. And it also runs very smoothly itself. And also it has less sharp increase or decrease. We can see that the online can be synchronized with the offline. And also, there's a typical example. We can see an increase of 65% from just 15% before. So this is a sharp increase. So for the offline task scheduling, it's to do with the characteristics of the task. So if it runs very smoothly, then the rate is very high. So the CPU utilization is not that high, and it won't reach a high level. So it's to do with the characteristics of the online tasks. So the conclusion is that the Tencent kernel group, we are focusing on the researching how to improve the integration utilization rate of the servers as the server is becoming larger and larger, and it is becoming more and more competitive. So we have more requirements for the scheduling, and network is also very important. Last year, we optimized a lot of servers last year, and yes, we need to focus a lot of areas. Why the offline cannot be realized to an acceptable level? Because new model, it emerges, it brings some problems. So BTD scheduling algorithm, what it is about? We need to classify the process. We need to classify the processes to divide them into offline and online. We need to make sure that to make it juggle with different tasks at the same time. How to increase the utilization rate of the CPU. this is the conclusion from our research. So I'm not sure about the patch, but I think there's not big change to it. CFS will be changed later, or will adopt our thought to classify. Otherwise, the utilization rate cannot be improved. This is our development plan, the draft plan, and finally we'll finalize the whole report. And I will, with detailed information, the Linux, the Tencent, we have released Linux, and you can buy it in the cloud. And this is our cloud headquarters, including our open source programs. This is Linux team. Yes, like the hybrid, the public and the private cloud. And we also have input in the nationalization of the device. So that's the end of my presentation. So yes, I may be running a bit faster because I don't go deep dive into these details. Otherwise, it will concern the scheduling of the kernel. If you are interested in it, you can pay attention to my slides. So in general, it provides a new thought for our offline task. So hello. Sorry, the interpreter cannot hear what he's talking because he does not turn on the microphone. Yeah, I'm from Alibaba. We have been working on this hybrid for a long time, and it's more about the scheduling of the CPU to ensure that the high operation level of the tasks. So the questions we have encountered is more about the memory. Yes, because the hybrid deployment machine is more about the offline and offline. And but after the mix, it will increase the memory, and it's a big increase because the utilization rate of the CPU will be increased. So there's a problem with management of the memory, and also because offline it needs to apply for a lot of the memories, then destroy it again, and it applies for it again. So the cache will be a lot, and it is to do with the recycling. So it will pose the impact on the host OS, and it will cause the deadlock for the online and some pressure for online tasks. So I think you have not dealt with it yet. Yes, this is about scheduling, optimization, and we also have done a lot of work on the memory. Like the recycling of the page. Yes, for each group, we have this page recycling. For the container, and for each group, it's overhead. We have these restrictions. If it had visited millions of files, then if we recycle it at a time, then it will be too late. So this presentation is about the CPU utilization rate. Hello? Sorry, the interpreter cannot hear what the audience is talking about because he doesn't use a microphone. So for the online tasks, Suppose you have 128 MB, and to make 100 of them online and 20 of them offline. We need to focus on the issue of the integration rate is too low. Yes, we need to focus on the utilization rate of the machine. Sorry, cannot hear you. I have a question. Yes, about the kernel, about the scheduling algorithm for this kernel, there's changes to it. How can you differentiate between the online and offline? How can you tell whether it's offline or online? We mark it on the page. It is a higher level scheduling. It has this offline scheduler, and it marks and it provides the interface. So you open the interface of the kernel and let it tell you, yes, the tasks, it is in cooperate with the upper level tasks. If you just screen this sample, I think the offline scheduling is conducted together with yes, I mean the upper level of the will give you this information about how to do this scheduling. Thank you very much.